The first example problem we're going to look at is 10.1. In this problem, we have a square-threaded power screw with single thread, and it's used to raise a load of 25,000 pounds. So the first thing we really want to pay attention to this here is that it's a square-threaded power screw. So square thread is going to help us when we take a look at some of the figures. The screw has a mean diameter of 1 inch. So again, this is telling us that the mean diameter is 1 inch, and 4 threads per inch. So it's giving us our pitch right here. The collar diameter is 1.5 inch, and the coefficient of friction is estimated as 0.1 for both the thread and the collar. So it gives us quite a bit of information within the problem statement, and asks us to solve for 3 different things. The first thing it asks us to solve for is our major diameter of the screw. Then it also asks us to estimate the screw torque required to raise the load. And lastly, it asks us if the friction, the collar friction, is getting eliminated, what is the minimum value of thread coefficient of friction is needed to prevent the screw from overhauling. So we'll have to look up what overhauling is and the associated equations and understand that we have collar friction and thread friction, and now they want us to eliminate the collar friction. So what we have here now is a schematic for the given data to illustrate in a visual form what we have going on for our problem. So this is a square-threaded, single-thread power screw used to raise a known load. So here's our known load up top here. Our W is equal to 25,000 pounds. Here's our F for our friction here. Here's our F sub C for the friction of the collar down here. Here's our D sub M here, our D sub C. So this just again gives us a visual representation of what's given in our problem statement. Now that we've had a chance to read through the problem statement and understand what they're asking us, the next step is to go through and write out all of our variables. What are the variable names? What are our values? What are our units? And what do these mean for our specific problem? So we use the same format that we use for all of our homeworks and exams. We have our givens, our finds, our assumptions. So within our givens, we know that this is a square-threaded, single-thread power screw that we're dealing with. We have our D sub M equal to 1 inch, which is our mean screw diameter. We have our pitch, given by variable P, which is 4 threads per inch, or the way that they like to show this is 0.25 is equivalent to 4 threads per inch. We have our mean collar diameter in the problem statement given to us as D sub C is equal to 1.5 inches. We have our coefficient of friction, where F is equal to F sub C is equal to 0.1. And we have our load, or W, is equal to 25,000 pounds. So this is all of our given information, the appropriate variable names, units, and now the next thing we need to do is figure out what are they asking us to solve for. So in this problem, they're asking us to solve for 3 different things. The first thing they want us to solve for is the major diameter of the screw, and this is going to be given as variable D. Second, we need to solve for the screw torque required to raise the load. So we're given this as capital T for screw torque. And lastly, they tell us if the collar friction is eliminated, or F sub C is equal to 0, they want us to find the minimum value of the thread coefficient of friction needed to prevent the screw from overhauling. So we're going to look for this as F. Only one assumption that we're making in this problem here is that the screw is not exposed to vibration. So this gives us our first page with all of our knowns, what we're looking for, and our assumptions. Now that we have all the given information from the problem statement and schematic organized neatly, the next thing we want to do is figure out how to start our solution to this problem. So in this case here, one of the things they want us to find in part 1 is the major screw diameter. So we need to figure out what is our key equation in order to find this major screw diameter. Well, this equation comes from figure 10.4. So stop here for a second and switch over to 10.4 in our book and see how we get this equation to calculate our major screw diameter. So now we go to figure 10.4 from our textbook. So 10.4 is power screw thread forms. So one thing to note here is that all threads shown are external, not on the nut. Now dm is the mean diameter, as we've defined in our problem statement as well, of the thread contact and is approximately equal to this equation here, d plus dr over 2. Now what we can note about this here is we have 5 different options here for the threading types. So we have A, acme, B, acme stub, C, square, D, modified square, and E, buttress. So from our problem statement, we know we're dealing with C, square. So we're going to zoom in on this, take a look at our variable names here, and see how we apply our equation. So now we take a look just at part C from this figure 10.4, and within this one, we have all the variables here labeled out for us. We have our D, we have our P, we have our P over 2 here, dm, dr. So we have everything that we need to plug into our equation here to solve for dm that we're going to use for the first part of our solution. So now that we've had the opportunity to go into our book and look at figure 10.4, we determined we could get this equation here from that figure, and we realized that we're dealing with part C for square. Now within this here, we saw all the variables, how they relate to the figure. Now we want to see how we can plug in our known variables from the problem statement for this here. So D, the major screw diameter, is equal to D sub m, our mean diameter, plus P over 2, where P is the pitch. So our dm is equal to 1 inch given in the problem statement here. And our pitch is 0.25 given our problem statement as well. So we can take these values, plug them back into this general equation from figure 10.4, and we end up with this here, that our major screw diameter D is equal to dm of 1 plus our pitch 0.25 over 2. We plug this in and we end up with that our major screw diameter is equal to 1.125 inches. So next we move on to part 2 of the solution. The second thing that it asked us to solve for in this problem is to estimate the screw torque, T, required to raise the load. So where we can start for this is we can go to equation 10.4a in our textbook, and we see this relationship here for torque. So T is equal to W dm over 2 times F pi dm plus L all over pi dm minus FL plus W FC dc over 2, where all of those variables we now know, where W is our load, we have a value of 25,000 pounds for W, so we plug in our W up here into this equation 10.4a for our load. D sub m is the mean screw diameter, so we have our D sub m here of 1 inch, so we can plug that into the equation above. F is the coefficient of friction for the thread. So anywhere we have an F up here, we can go in and plug 0.1. F sub C is the coefficient of friction of the collar. So F sub C is still 0.1. F is equal to F sub C. DC is the collar diameter of 1.5 inch. So we can plug in 1.5 inches for D sub C here. And L is the lead, which in our case here is 0.25. So we can plug that back in to equation 10.4a to solve for torque. And when we plug these in, we end up with this relationship here. T is equal to our 25,000 pound load times our dm here value, which is 1 inch, divided by 2, is equal to our F for the coefficient of friction of the thread of 0.1 times pi times our D sub m here, which is 1 inch. So we can plug that in for our mean screw diameter, plus L, which is 0.25, all divided by pi times dm of 1 minus the friction here, F of 0.1, times over here 0.25 for L, for our lead, plus 25,000 load times our 0.1 from our F sub C there, and 1.5 for our DC there, diameter of the collar, all divided by 2. And we plug this in, do out the math, we end up with our screw torque required to raise the load, T, is equal to 4,138 pound-inches. So we do our unit analysis out for all of these. We find out that this does come out to the correct units. Now we move on to part 3 of the problem. The third thing that it asks us to solve for is the minimum value of thread coefficient to prevent the screw from overhauling. So now we need to find an equation related to overhauling. So what we look at is equation 10.7a. So now we'll go to the book and take a look at 10.7a. So 10.7a comes from section 10.3.3 in our textbook, overhauling and self-locking. So a self-locking screw is one that requires a positive torque to lower the load. An overhauling screw is one that has a low enough friction to enable the load to lower itself. That is, negative external lowering torque must be maintained to keep the load from lowering. If the collar friction can be neglected, so equation 10.5, for a torque greater than or equal to 0, it shows that the screw is self-locking if the following conditions. So we jump to 10.7a for this for a square thread. So this simplifies down to F is greater than or equal to L over pi dm. So this is the equation that we're going to use to solve the third part of our problem. So using that equation that we found in 10.7a in our textbook, again we have F greater than or equal to L over pi dm, where L is our lead of 0.25, dm is 1 inch, which is the mean screw diameter. So we can plug those in now, and we have the F is greater than or equal to 0.25 divided by pi times 1 inch. So F is greater than or equal to 0.08 when we do out the math. So the minimum value of the thread coefficient of friction needed to prevent the screw from overhauling is 0.08.